Welcome back, welcome back, welcome back. I am Miss Lisa. This is my YouTube channel where we talk about science and math. Today this is physics, and we're going through this book, but if you like the way I explain things, you don't need that book. This is a class primarily designed for homeschoolers, but you don't have to be a homeschooler to watch this video. But if you want to do it as a class, you should get that book and do the homework that's in the descriptions. We've reached the point in physics where each chapter has two videos. It has one where I talk through the concepts, which is what this one is. We're going to be talking about universal gravitation today. And then there's another one where I do the math problems where instead of seeing me, you see my calculator and the problem up close. So especially with the calculator one, stop it, do it on your calculator to make sure that you can get the same answer I get on your calculator. So you need to do that. If we were face to face, I would make everybody get their calculators out in my class, and then they would do it, and I make the kids show me their calculator that they got the answer on it. And then sometimes they don't, and they look at me with big eyes. And I'm like, do you have on your calculator? No. Then we got to get it. And usually, by that time, the kid next to him has it and can show them, look, push these buttons. So you need I show this on a TI-84 graphing calculator. So that's what I recommend you get because you can use it all the way through college. It's the last calculator you have to buy, and it does so much. So that's the one I recommend. All right, so like, share, subscribe. I have a goal of 1,000 subscribers so that I don't have to record and then upload. I can just do it all at once with YouTube Live. That's what I want. I want this to be easier. All right, so get out your book, and we're going to talk about gravity. And one of the things that I made my kids do last year was I made them go find the Schoolhouse Rock video on gravity because it's really good. Watch it after we talk about this chapter, and after you read it, go watch it. But it has got the math in there, it's got the concepts, it's got the physics, it's really good. It's the one that goes, and I can't sing good, so just be warned. Down, 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 gravity. That's the one you're looking for, okay? It's got Mary Jo and some boy or in the 50s. So watch it, but not yet. Or maybe watch it now. Maybe go watch it now and then come back and watch it again at the end once you understand everything about it. But it's really good. One of the best Schoolhouse Rocks. Not all of them are good. Some of them are like, this isn't really telling me anything, but that one's great. All right. So why, if you look at your book on page 155, the bottom line says, the question of why objects attract each other is still not answered. So we don't completely understand gravity. Which your takeaway is, it was the same thing I was telling physical science when I was making videos, that not everything is understood in science. And there is a lot still to learn. My son, Nathan, is in graduate school at Georgia Tech, and he was listening to a biochem professor talking about how we don't even understand the liquid inside the eye at all. That it is just not understood. There's all these proteins in there that should not be doing what they're doing. They're supposed to not like water, but they are interacting with water, and there is just so much we don't know. And this professor was saying, that if we could figure this out, it could help people see. It might be something that would have an effect on vision, which could bless lots of people. So don't get the misinformation that science is settled, everything's been discovered, there's nothing left to discover. And also, don't get the idea that scientists agree. Scientists disagree all the time. Any position, you'll find a scientist to take it, and another scientist who'll say, no, that's not right. So just know that it's not as settled as sometimes maybe the media makes it sound. I think real scientists know we got a lot to learn still. All right, so gravity. Now, you've heard Isaac Newton discovered gravity. Not really. People had been seeing things fall for a long time, but he started figuring out the math. Remember way back when we started this class that I told you that there are certain things in physics called laws. They're the laws of physics. And they're so true to their math. They have a formula and they usually have a constant with them. And gravity is one of those. So watch part 2. We're going to be doing some math, some gravity math. Okay, so look in your book on page 156. And it starts really with a guy named Tycho Brahe. And he was from Denmark. And he saw an eclipse, and he decided to be an astronomer. So he was the first one to really make precise measurements of all the planetary, all the planets. He was in the 1500s, and 1560 was when he saw the eclipse. And so he started being an astronomer. And he believed that the Earth was the center of the solar system. So he didn't realize that, what modern people do. And he even talked the king into giving him an island so he could make an observatory. But then he fell out of favor with the king. Supposedly he was hard to get along with. And then he goes and he works for another king. And while he was there, he had a student named Kepler. And Kepler started using all of the data that the first guy made and applying it to his idea that maybe the Earth isn't the center. And he started coming up with what are called Kepler's laws. So if you look in your book on page 157, you see Kepler's laws. The first one is that the planets are ellipses with the center as the sun. Let me translate that for you. Okay, so a circle, that's not a circle, but you can imagine it is. A circle's this shape. If you have an oval, it's called an ellipse. And if we were face to face, I would have you do this, and it's a lab that you're going to do if you do it. But if you take a piece of cardboard and you took 2 push pins and you put in them, and then you put a string around them that's, push pins with like a loop of string, like the push pins are here, and we put a loop of string around them. And then you take your pencil and you go around stretching it out as far as you can that the string will let you inside that circle. The shape you draw is a special oval called an ellipse. The push pins are the focus, or the foci, which they're a special geometry relationship. And you can learn more about this by watching the geometry videos on it. But that these ellipses, Kepler figured out, were, and you can see how you're going to draw your ellipse on page 158 if you want to flip over there and see. This is the shape of the orbits. The orbits where the planets go around the sun is at one of the focal points, at one of these focal points. And so we go around, not in a circle around the sun, we go in this oval. Now, the second thing he figured out, you need to look in your book at the picture on page 157. If an imaginary line from the sun to the planet sweeps out equal areas in equal time intervals, thus planets move fastest when closest to the sun, slowest when further away. So the reason why I want you to look in your book is it looks like a sun with sunbeams coming out, and the sun's at one side. Well, each of those little triangles that are either orange or yellow going around, they're all equal areas, and some of them are short little triangles and some are long skinny triangles, but if you figured out the area of the triangles, they would be the same. So it makes it where when the planet is up close to the sun, it goes faster because it's close and they have to be fatter, so they go faster. And then when it's far away from the sun, it goes slower. And it's kind of like things whip around these things. And that's what they used. You see it sometimes with space stuff where they'll whip around something. And that's what the planets do. They whip around the sun. So that's another thing and that he figured out. And then the last one is this math equation. And it is the squares of the periods in a ratio equals the cubes of the radius, the radii. That probably didn't make any sense, but I'm going to show you the math. And it's just that there is a ratio relationship between period and radius if you have two different planets or bodies or something like that, you can figure out this relationship between the period, the time it takes for one revolution, and the radius. Okay, so we will be looking through the math of that, and that is going to be our first example problem that we're going to do in the second. Okay, the next idea is universal gravitation. So this was in 1666, 45 years after Kepler's work. This is when the plague hit, and Newton went and he figured out calculus and his laws of motion and gravity. It's just unbelievable that one person figured all of this out. And during the plague, we're having the coronavirus right now. I haven't figured out anything great. I've taught a lot of kids a lot of stuff virtually, but I've not figured anything out. Nothing great in science. So our little plague's not being very profitable in my life. Maybe someone else. Someone's figuring out everything in physics while they're in quarantine for coronavirus. Okay. So he figured out that, let me read it to you so I get it right. Newton had used mathematical arguments to show that if the path of a planet were an ellipse, in agreement with Kepler's first law, then the net force F on the planet must vary inversely with the square of the distance of the planet and the sun. So he came up with an equation, okay, that has to do with a proportion. The symbol for proportion is this. I remember when I went to college, we did not learn that in my high school physics. I went to college and saw that and said, great. I am so unprepared. They have math symbols that I don't even know what they are. Well, it just means it's proportional. It means that you can set up a ratio, that it's proportional. And it's that the force is 1 over the distance squared. And I'll explain that to you. Don't panic. It's going to be okay. Okay, so look in your book on page 161. And there in the little box is this equation that he proposed, that the force equals big G. And little g is what we've been using, 9.8 meters per second squared, the acceleration due to gravity. Big G is the universal gravitation constant. It's a different number. It's just a constant that we're going to fill in. It's just a different one. So don't get big G and little g mixed up. Okay, and then you multiply the two masses divided by the distance squared. The main thing that you need to take away from this is the pictures. They're on the bottom of 161. They show what effect mass and distance has on gravity. And if you have more mass, you have more gravity. If you have more distance, you have less gravity. That's the big thing. And in particular, it's this ratio that he figured out, this proportion that he figured out. So on the first one, they have the Earth and the Moon. There are a certain distance, and the gravity between them is a certain force. If the Moon was twice as massive, and the Earth stayed the same, the gravity would be twice as much because you've got more mass on one side, it makes it twice as gravity, the force. If the Earth is the one that became twice as massive, you would also have twice the force. It doesn't matter which one becomes twice as massive, it doubles the force, okay? If they both became twice as massive, you'd have 4 times the force. It'd be 4F. I know this looks funny, me looking through my glasses at you, but it's just, it is. But for all of these, the distance stayed the same. Now let's talk about distance. If you've got a certain force between the Earth and the Moon and a certain distance, if you doubled the distance, you would only have 1/4 the force. And it all goes back to that distance squared in the denominator. It's what the effect that math has. If you halved the distance between the Earth and the Moon, we'd have 4 times the force of gravity. So, and it all has to do with that squared thing in the denominator. Okay, so that's the big takeaway. So we have some forms. So so the equation, this led to Kepler's third law equation. The square of the period is proportional to the cube of the distance. And Newton found that this was also true. Kepler had thought the path was a circle. Newton figured out that it was elliptical, and it still worked. The math still worked. Okay, then they figured out how to weigh the Earth. You can read about that, the experiment for that. That was interesting. And the big equation is on page 163. It's the force is equals to the universal gravitational constant times mass 1 and mass 2 divided by the distance squared. So big G is the universal gravitational constant. Okay, and I'll be showing it to you in math. Okay, so this is the next concept. Okay, and it is satellites and orbitals. Okay, so imagine that you have a giant mountain so big that if you shot a cannon off of it, its trajectory, its curved projectile motion would be so great that it would be past the Earth and it would fall next to the Earth. Okay, can you imagine that? Because of gravity, it would keep going and it would just go around and around the Earth, always falling by the Earth, but never reaching the Earth because it's too far out. It's always falling because of gravity, but it doesn't hit the Earth because it's always falling next to the Earth. That's how satellites work. We don't have a giant cannon to shoot them out. We put them up there with the space shuttle. Space shuttle takes them out and lets them go. And they're falling around the Earth at all times, constantly falling. But if you imagine the cannon, sometimes it's a little easier. And they've got a picture of that on page 164. And we're going to do some math with the velocity of a satellite using the universal gravitational constant. Okay, so now here's the next thing. Okay, so do you remember what I told you is making this fall? It's gravity. And now we send, what did I tell you? They send up there to let out the satellites? Space shuttle, the astronauts. I just watched a documentary. It was a bunch of parts to it about the space shuttle blowing up with the teacher on it. It was very sad. Krista McAuliffe, I think was her name. But anyway, I recommend it. Y'all should watch it. It's very interesting. It actually has a lot to do with this. But it's long. I'll let you know. It's like 6 parts. But I found every part interesting. And now I'm wanting them to do one of those on the other space shuttle that blew up, the one that busted up over Texas. But anyway, back over here. Okay, so what is pulling on this? Gravity. But when you see those astronauts up in the space shuttle, they're floating around weightless. It's like they're way, way deep in space where there is no gravity, but they're going right around the Earth. You see the pictures. And where there's gravity pulling on them. Why can they float around the space shuttle like that? The reason why is you have to go back to what I told you before. The satellite, the thing we launch around, is constantly falling. So you got to think about cartoons. Okay, in a cartoon, if the elevator's falling, you know how Bugs Bunny floats up and he's floating in the air like that? Well, that would be true if but normally Bugs Bunny and the elevator would fall together like this. But if Bugs Bunny was up in the air and the elevator's falling, it would be like weightlessness. It would be constantly falling together like that, and it would feel like weightlessness. So it's like they're weightless and far out outer space. But the reason why is because they're all falling together, going around the Earth. So there's not the gravity pulling down on them because they're falling. They're all falling together. So you can read about that in your book too. It's pretty interesting. Okay, so here's our next idea. Newton sort of had a hard time even with the ideas he discovered about gravity. He's like, what is this force? How does it do it? How can something as far away as the sun have a force that's reaching the Earth that's so far away? And the answer really goes back to Michael Faraday. He is the one who came up with the idea of fields, magnetic fields, electrical fields, and then they realized that there could be a gravity field. So the Earth. So then there's this idea of a field that is a force around the Earth and around everything that has mass. It has a field of gravity. Now, like I've got one, but I'm so small, I'm not massive enough that I can't attract anything to me with gravity. But the Earth is massive enough, the sun is massive enough that they have a field of gravity big enough that it can be felt. It can make things fall to them. And so now the next person who had an idea about this was Einstein. And Einstein said that that gravity is not a force, but an effect of space itself. According to Einstein, a mass changes the space about it. Mass causes the space to be curved, and the other bodies are accelerated because they are moved in curved space. So there's a little picture in your book where a guy's got a rubber sheet and he drops it with like a graph paper design on it, and he drops a ball in it and it curves to the ball. And then if he drops something else on there, it would go down toward that other ball. It would be accelerated to it. It would be a force of attraction, because that one ball is pushing the rubber sheet down. And if you did an angle, it would go around and around it. So that's Einstein's idea. And it had a lot of skepticism. But we have seen in telescopes light bending the way he said it would. We've seen it where with black holes where light bends toward it. And so the bright galaxy bent as it passed a closer dark galaxy. So Einstein seems to be right, but the book says Einstein's theory is not yet complete. It does not explain how masses curve space. Physicists are still working on understanding of the true nature of gravity, and that's still true to this day. We still don't understand gravity completely. Gravity is a bit of a mystery. It's not all figured out. We've been learning about it for hundreds of years, but we don't have it all figured out. So come back for part 2 and we'll do the math. We'll do some gravity equations. And remember, science is great, math is great, physics is great. Like, share, and subscribe. I'm Miss Lisa. See you soon.